And the next speaker will be Odette Scharenborg. She is associate professor in the Delft University in the Netherlands, and she is working on the multimedia computing group, focusing on speech processing algorithms inspired by human speech processing, with a lot of amazing work, most notably in non-nativeness and multilinguality and dyslexic speech. I will ask Daniel to play her recorded video, but she will try to do her best to be in the Q&A session if we will have any questions.
Yeah, I will play the video. Can you see it now?
Yes, play. Start playing. Thanks so much.
Thank you for the invitation to give this talk. In this talk, I will be talking about unsupervised subword modeling using cross-lingual phone-aware modeling. This work was carried out by Simon Feng, who is a former postdoc in my lab. As you know, there are around 7,000 languages in the world. However, for only around 2% of these languages, automatic speech recognition systems have been developed. This is due to the fact that for by far most languages in the world, not enough training material is available to train the acoustic models. Therefore, conventional supervised acoustic modeling techniques cannot be applied directly. To facilitate ASR technology for low resource languages, investigation of unsupervised acoustic modeling, or UAM methods, is necessary. Unsupervised acoustic modeling aims to find and model a set of basic speech units that represents all the sound in a language of interest, that is a low resource or target language. A strict assumption of unsupervised acoustic modeling is that for the target language, only raw speech data is available, while the transcriptions, phoneme inventory and its size, and pronunciation lexicon are unknown. This is known as the zero resource assumption. There are two main research strands on unsupervised acoustic modeling. The first strand formulates the problem as discovering a finite set of phoneme-like speech units. This is often referred to as acoustic unit or acoustic model discovery. This is in essence the ultimate goal of unsupervised acoustic modeling. The second strand formulates the UAM problem as learning acoustic feature representations that can distinguish subword units of the target language and is robust to linguistically irrelevant factors, such as speaker information. This research strand is often referred to as unsupervised subword modeling. In essence, the second strand is focused on learning an intermediate representation towards the ultimate goal of unsupervised acoustic modeling. The two strands are closely related and they're connected and they can benefit from each other. For instance, a good subword discriminative feature representation has been shown to be beneficial to acoustic discovery. While conversely, discovered speech units with good consistency with true phonemes are helpful to learning subword discriminative acoustic feature representations. In this talk, I'll present our work investigating the possible benefit of acoustic unit discovery and unsupervised subword modeling and vice versa. The first study I'll present shows the benefit of acoustic unit discovery for supervised subword modeling. For the task of unsupervised subword modeling, we proposed a two-stage learning framework. At the first stage, which is the front end, we train a self-supervised representation learning model named autoregressive predictive coding, or APC. APC preserves phonetic, subword, and speaker information from the original speech signal, but makes the two information types more separable. This aspect makes APC a possibly interesting method for unsupervised subword modeling. At the second stage, the backend, a cross-lingual out-of-domain DNN with a bottleneck layer is trained using the APC pre-trained features as the input features. The second stage creates the necessary frame labels, which are missing due to the zero resource assumption. Visually, this is what our systems look like. First, the training phase. Of our target language, in our case English, indicated in the pinkish box on the left, we have a certain amount of untranscribed speech training data. We then trained the APC model front end with the untranscribed target speech in a self-supervised manner. After training, the pre-trained features of the target speech are extracted. At the back end, an OOD ASR system assigns one phone label to every frame of the target language's speech. In two different experiments, this OOD ASR is trained on Dutch or Mandarin. The DNN-BNF model is then trained using the APC pre-trained features and cross-lingual phone labels as input and target in order to learn subword discriminative features for the target speech. During the test phase, here on the horizontal line, a DNN-BNF model is used to extract BNF representations for test data of the target language. These BNF representations then are the subword discriminative feature representations of the target language's speech. The APC and DNN-BNF models were trained using different subsets of LibRe-Lite with different sizes, as we were also interested in the effects of the amount of available untranscribed data for DNN-BNF model training. We trained two different OOD systems, as I just said. A Mandarin OOD system trained on 140 hours of read speech from the Eidertatang corpus, and a Dutch OOD system trained on 483 hours of multiple speech styles from the spoken Dutch corpus. We tested our system on the 4 test sets of LibRe-Lite and on the Zero Speech 2017 corpus in order to compare our approach with previous research in this area. We ran 2 types of experiments. The first experiment investigated the effect of the proposed APC training in comparison to a system without the APC training on the task of unsupervised subword modeling. To that end, we compared APC features with MFC features as the front end. Secondly, for low resource languages for which transcribed data are absent, even unlabeled speech can be costly to collect. The robustness of unsupervised subword modeling methods against limited amounts of training materials is therefore an important topic. However, not many people have looked at this yet. So we did this. And we varied the amount of unlabeled training data between 600 hours and 6,000 hours. Moreover, we carried out a detailed analysis into how well phoneme and signature feature information of the target language is captured in the representations. Unfortunately, I will not be going into detail about this, but the results can be found in our paper. So, a summary of our results. We evaluated our systems on the unsupervised subword modeling task using the ABX error rates. We found that the proposed front-end APC pre-training outperformed the system with only a DNN-BNF backend, which used MFSC features as input. We found that using Dutch OOD labels outperformed using Mandarin OOD labels. This is possibly due to the larger similarity of Dutch than the Mandarin with the English language. We found, not surprisingly, that performance increased with increasing amounts of training material. Interestingly, the performance of our best system, which was trained with 6,000 hours of untranscribed training data and used labels of the Dutch OOD system, is very close to that of a supervised system trained on 1,000 hours transcribed data of our English target language. This implies that APC pre-training saves around 5,000 hours of training data, making APC pre-training highly appealing in low-resource speech modeling. The effect of pre-training on the needed amount of training data is even larger when Mandarin labels were used. For Mandarin, over 99% of the training data was saved in this way. So this table on this slide shows our ABX results on the Zero Speech 2017 English dataset. The top line system from the challenge is in the second row from the bottom, indicated with a 1. The best performing model using OOD data is shown in the bottom row, is indicated with 10. Both these systems use labeled target data. So our proposed system, which uses APC pre-training, beats these two systems without using labeled target data. So our best system indicated here in bold in the top row. And these results just show the benefit of using AUD techniques for unsupervised subword modeling. So now the reverse. The next study shows the benefit of unsupervised subword modeling for acoustic unit discovery. For the task of acoustic unit discovery, we combine unsupervised subword modeling with acoustic unit discovery in a new two-stage learning framework. The first stage consists of the two-stage framework presented in the first half of this talk, which creates frame-level subwords discriminative feature representations. The second stage applies k-means clustering to the subword discriminative feature representations from the first stage to obtain a set of clusters. Each cluster resembles a phone-like acoustic unit. The outcome of the proposed two-stage approach are then the discovered acoustic units. As said, the first stage is similar to the system I just presented, but with a few modifications. We now use a multilingual OOD ASR because different languages have different phoneme inventories. So multilingual OOD phone labels capture a more extensive set of sounds. This makes them, in theory, more useful for acoustic modeling of a target language. Our multilingual OOD system is trained using 5 global phone and 8 YARPA Babel languages. Moreover, we again used APC and MFCC features to train the DNN-BNF. The experiments comparing the APC and MFCC features showed the system with MFCC features performed best. So this was used in our best system. The second stage is a segment-level clustering stage. For segment-level clustering, we need phone segment boundaries, and these are estimated using the OOD ASR. Moreover, the segments need to be represented as fixed dimension vectors. We compare 2 approaches to create these fixed dimension vectors, average-based and downsampling. Experiments comparing the 2 showed that the average-based method outperformed the downsampling method to create the fixed dimension vectors. As a segment-level clustering technique, we used k-means. Where in the previous study we used English as our unlabeled target language, in this study we investigated AUD for a real low-resource language, in this case, Mboshi. The Mboshi database consists of speech from 3 speakers who produced 5,100 sentences, which resulted in about 4.5 hours of speech. And these are our results. This table shows the results of our proposed 2-stage system on the task of acoustic unit discovery and 2 state-of-the-art systems. We evaluate using 2 metrics, normalized mutual information or NMI and F-score. NMI captures the statistical dependency between discovered units and ground truth phone units, and a higher score is better. The F-score measures the accuracy of the phoneme segmentation, and we use a tolerance window of plus or minus 20 milliseconds. Also here, a higher score is better. The results show that our best model, which employs 13 OOD languages in stage 1 to provide phone labels for target language AM training and uses an average-based method, segment clustering in stage 2, outperforms state-of-the-art performance on a very low resource database, in this case, Mboshi. And this is indicated here in bold. And this model used 60 clusters in the k-means clustering. So when we compare our results to an identical system, which has access to accurate phone boundary information, we observe a 16% NMI performance gap with our best system without the golden phone boundary information. And this gap shows the importance of having accurate phone boundary information for clustering the segments. To wrap up, in this talk, I presented 2 studies to highlight the mutual benefit of combining acoustic unit discovery and unsupervised subword modeling. The first study showed that acoustic unit discovery benefits unsupervised subword modeling by providing pseudo-phoneme-like unit labels. The second study showed that unsupervised subword modeling benefits acoustic unit discovery by providing a better separation between sounds and spectral features. Finally, both our proposed 2-stage frameworks, the one for the unsupervised subword modeling task and the one for the acoustic unit discovery task, show state-of-the-art performance on their respective tasks, further showing the mutual benefit of combining acoustic unit discovery and unsupervised subword modeling techniques. Thank you for your attention.
Thanks so much. I'm happy that we listened to Odette's great presentation and great work.